Okay, this is 5.2 identities. These are some identity methods that you're going to see over and over again. The first one is the perfect square. And you can see up here that I have two of the quadratic perfect squares, and I'm going to go ahead and multiply those out. So I would have a plus b squared would be a plus b times a plus b. And if I multiply that across, I would get a squared plus ab plus ab plus b squared. So I would have three terms, a squared plus 2ab plus b squared. And I wanted to show you that you can get the same thing without multiplying it out like this, without writing it out and multiplying it out. If you'll notice that if it's a perfect square, the first term is just going to be a squared. The last term will be b squared. To get the middle term, you would do a times b and double it to get 2ab. And so if we use that same scheme on this next one, we would have the first term would be x squared, the last term would be 4, there will be a plus in between, and 2 times x is 2x, doubled is 4x, and you would have the same thing. And if you can learn to do it that way, it saves you a lot of steps. All right, same kind of deal here. We have the secant squared minus 2 secant x plus 1. You can see that that is also a perfect square. And so when I write it like this, this will be secant x and 1. And because this is a minus sign, this will be minus. And so if we were to multiply this out, remember that the first term was secant squared x. The last term would be 1. The middle term would be secant times negative 1, which is negative secant x doubled, negative 2 secant x. And we can do the same thing then with this cosine. I'm going to have something squared. Normally this would just be cosine x plus 1, right? But because this is cosine to the fourth, this is going to be cosine squared x plus 1. And so that is a perfect square. And so that shows you how you can factor it if you recognize the perfect square. Not always a perfect square, but when it is, it's really handy to know how to factor it. Likewise, you can have the difference of two squares. So for instance, a squared minus b squared would be factored a plus b, a minus b. And you can multiply that out to see what happens to the middle term. That's the same thing as a squared minus ab plus ab minus b squared. And you can see that the middle term goes to 0, and that's why you don't have it. So you can factor these as well. So you can say, instead of it being a and b, it would be secant, and then a 1 and a 1, and then just alternate the signs. And I don't know, plus, minus, minus, plus, it matters not. You can do the same thing on here. I can factor a secant squared x, secant squared x, cotangent squared x, cotangent squared x, and then minus and plus. And one of those actually goes to 1, if you remember the Pythagorean identity. Here's a common technique to turn something into the difference of two squares. You start off with something nothing squared at all. You can multiply times a form of 1, and the difference of two squares is in the denominator. You can see it in the denominator here. This is 1 plus sign, 1 minus sign. So when you go ahead to multiply that out, generally I would just leave the top like this, and then the bottom would be 1 minus sine squared theta. If you'll recognize that that's the difference of two squares, that's why we use 1 minus sign instead of 1 plus. This, you know, can be substituted, so this would be the cosine theta, 1 minus sine, I'm getting in a hurry, minus sine theta, just rewriting the numerator, over cosine squared theta. So this and this cancel, and I'm left with 1 minus sine theta over cosine theta. So my original problem, this is an identity because they equal each other. Now here's one you don't see often, and that's factoring the sum and difference of cubes. And this is a review from algebra. But basically it's a pattern. So if I have a to the third plus b to the third, then I would factor this by writing a plus b. So I would write a plus b without the same symbol, these are the same, right? And then without the third. And then over here, the first is always going to be a squared, the last is going to be b squared, and the sign in front of the b squared is always going to be positive. This is always positive. And then this sign right here will be the opposite. These will always be opposite. These will always be the same. And then just a times b, and you're done. Okay, so for instance, x to the third minus 1,000 is x to the third minus 10 to the third. So this is the a and this is the b. So if I'm writing this out, this would be a minus 10. This would be x squared. This would be 10 squared. This is negative, so this will be positive. This one's always positive, and then this would be 10x. So in other words, this is x minus 10, x squared plus 10x plus 100. And this, of course, never factors. That's why it's not 2. It's not a perfect square at all. It never factors. So if I do this bottom one, I'll change color. To the third power, this would just be 2x. 8x to the third is 2x quantity cubed. And then 343, if I remember correctly, is 7y. Going to check. Yes, that's correct. So to factor that, you would do this same scheme, and I would do 2x minus 7y. This would be 2x quantity squared plus 2 times 7 is 14xy. This is always plus, and then this is 7y squared. So if I write it out, this is the most complicated part of it, 4x squared plus 14xy plus 49y squared. So work through that and see what you see, but that should be a review. Okay, so now we'll use that same principle using trig functions. So looking at tangent cubed minus 1, I'm going to rewrite it like I did on the other page. Tangent x quantity cubed minus 1 quantity cubed. So this is your a and this is your b. So when you go to write it, you do tangent x minus 1, same sign. The first term is always the first a squared, right? Tangent squared. The last one is 1 squared. There's always a plus in front of the 1, and then it's the opposite sign, so that's also plus, and then multiply. Okay, looking at the same thing here, secant cubed, tangent cubed, and you knew that you're going to have to do something different to it because it's not the identity. The Pythagorean identity is squared. All right, so once again, I'm going to rewrite this. So I have secant x quantity squared plus tangent x quantity squared. Once again, this is the a and this is the b. And I'm going to write it down here where I have a little bit more room. But I have secant x plus tangent x. All right, then the first term is secant squared. The last term is tangent squared. This is always plus. This is the opposite sign, so this is minus. And then this middle term, if I have room to squeeze it in, is secant x, tangent x. All right, and so that's what you have. And that's with the difference or sum of cubes. This is a reminder about cofunctions. We've talked about cofunctions before. Over here on this right triangle, you can see here that I have theta. This is a right angle. This other acute angle is just going to be 90 minus theta, or in other words, pi over 2 minus theta. And so that's the cofunction. And remember that the sine of this other angle is equal to the cosine of theta. And the cosine of this other 90 minus theta angle is equal to the sine of theta. And those are just the same cofunction identities that we've done. That's just sine and cosine. You know there's others. Okay, so for instance, over here, if I have sine squared of 35 degrees plus cosine squared of 35 degrees, what you notice here is theta is 35 degrees. Right? So the Pythagorean identity says that the sine squared of 35 plus the cosine squared of 35 is 1. Because 35 is theta. So 35 can also be written as 90 minus 55. Right? 90 minus 55 is 35. So the sine squared of 35 could also be equal to, notice that this is the sine squared of 90 minus theta, right? So it would also be equal to the cosine squared of 55 degrees, because 35 and 55 are cofunctions of each other. All right, so on this green one down here, if I have, I might be able to write in green, that would be awesome. Then that would be the same thing as the sine squared of 90 minus 70 degrees. That would be 20 degrees, right? So this would be equal to the cosine of 70 degrees, right? The sine of 15, sine squared, would be the same thing as 90 minus, that would be 75. So this would be equal to the cosine of 75 degrees. So the sine of 35 degrees is going to be equal to the cosine of 55 degrees, and so on and so forth, because you're looking at actual angles there for the cofunction. So here is an example of what you would use to evaluate something without a calculator. Okay, so what we have here is we have two angles. We have 35 degrees and we have 55 degrees. And I know that 35 plus 55 is equal to 90 degrees, right? These are degrees. I should say degrees. Okay, so what I can do is I can rewrite one as a cofunction of the other. So for instance, 35 degrees is 90 minus 55 degrees, right? So that means that's 90 minus theta. So that would be equal to the cosine squared of theta, which is 55. Well, the cosine squared of 55 degrees plus the sine squared of 55 degrees is 1. Remember this? Cosine theta plus sine theta equals 1. And my theta in this instance is 55 degrees. So what you're doing is you're taking the two angles and you're noticing that they're cofunctions of each other, and you can then assess this without a calculator. All right? Be sure that you have all of these examples in your notes, every one of them. Use this as an opportunity to practice some of these things. Try to get this cemented into your mind as to what a cofunction is and what that should look like. There's a lot to memorize, and if you're not memorizing them or memorizing them as you do your homework, then you're not going to remember them for a test. Okay? See you in class.